I check out this change work. So once you have your assignment A ready, please convert the assignment number into 9. Okay, eventually you will submit assignment 9. To the saver, so I can grade it. So let us prepare the framework first. So turn on to the 8, change it to 9. So as you can expect, once we complete this assignment, definitely you will have your GA library ready. For binary automation problem, also for permutation automation problem. For example, TSP is another sequences automation problem too. All right. So change the average file name into probably 9. Even the folder name, in order not to confuse with your previous. But for the GA solver, it's okay because we keep updating it, so it's all right. So that is your GA solver, right? So basically, the executable code should be a DLL. It's not executable at all, but it's a library. So later on, you can use this library to solve all kind of different kind of problems. So right now, the goal for this assignment is try to complete this GA solver. That is your GA solver. Remember that. So later on, you can keep adding different kind of encoding GA there, and then making your making your solver library complete. So right now, assignment 9 just use the GA solver, the binaries and the permutation GA solver to solve the job assignment problem for us. Okay, so remember that actually we are kind of building the library simultaneously and also the one application, right? Okay, so change the file name to 9, and there's another project file right here. So change it to 9. Okay, so let us check about the solver. Solver is okay. It's just a C# project, right? So it's our GA solver, so it's okay. But before you open it, you should modify the contents of the solution file first. So I might add a text file, then pop it out, update the content of the solution file first. So kind of find 08, right? Right here, it's a project name. So another line, next, it's a pass, right? So to 9. Project file name, right? 9. That's it. I think it's probably should be 3 press needed to be updated 090909. That's it. So we save it, the file. All right. So probably that will be all. Okay. Yeah, project file there. So we open the solution file, then. So by the time you should check out the explanation, the instruction or the assignment 9 from the saver, okay? So otherwise, I will send the file to your desktop if you are using the computer or the lab. Okay, later on. So just wait for me. So I don't need this anymore. So I terminated broadcasting. Assignment 9, okay, right here. So I sent this file to your desktop. The desktops or the computer in the lab, because you can pick them up. Otherwise, you just download it from saver. So later on, we need to study the contents of the instruction. So I use Windows broadcasting. All right, so we have our project ready. 罗君在吗？那个 complete 吗？功能 complete 吗？动画什么？好，不要紧，我们不 care 完全正确哈。好 ，ready 就好。Okay, so let us read the instruction. I mean, the instruction to discuss about the problem, automation problem. We need to model that into a different kind of automation model. We try to model our job assignment problem into a binary optimization problem. So the variable turn out to be binary. So in that case, we can use our binary GA to solve it. All right. So let me show you the instruction. Okay, so in the assignment line, you are about to complete permutation GA. That is the new one, right? Binaries we have actually, I think if you implement it, actually in assignment 8, it is complete. So right now we can use binary GA to solve our job assignment problem. But since you intended to use the binary GA, right? So you need to model your job assignment problem, not in the previous way, because in previous way we use brute-force method, right? So actually, it's a solution to the job assignment problem. Actually, it's a sequence of integer, right? But in that case, it's harder to solve it. I mean, in linear optimizations solver, right? We cannot use simplest method. Okay, probably I should ask you guys. I mean, for those students are not from IE, please raise your hand. All right, let me see it. If you are not from IE department, please raise your hand. All right, okay, put it down. Have you ever learned anything about linear programming? Did you, or in other words, have you taken any design automation courses or not? All right, so do you have any idea about so-called simplex method? Okay, I saw her not. How about the other students? No? Okay. Never mind, I mean, I'm a mechanical engineering guy too, all right, so it's a long time ago, all right, so but then in that case we have a course called design optimization. So that is related to the design, I mean, practice somehow. But anything about automation, any courses that talk about automation, definitely it should start with a so-called simplex method. Simple method can solve the linear automation problem. Anyway, so the problem is that you have an objective function. The function is in terms of their variable, I mean, or in terms of their decision variable, the function is linear. And also, under this objective function, there are several constraint equations. Either it is equality or inequality constraint. And that constraint equation is also, in terms of the variable, should be linear. So if you have a linear automation problem, you can use that method, so-called linear programming method to solve it. And in fact, right now, you do have, I think you do have this linear solver. I mean, later on I will show you how to do that. I mean, if you did not study, you don't have any idea about the so-called linear programming problem. But it's okay. I mean, now I will guide you. I mean, using the Excel application step by step later on, right? Okay, but for the IE problem, it's okay because they have a core course called research operations research. So in operation research, a lot of parts is talking about the so-called linear programming. All right. So skip the first part first. Let us directly go to this problem, job assignment problem. So right now we try to solve this problem using binary generic solver, GA solver, right? So you need to turn this automation turn that to be a linear. Well, actually, it's a binary and linear automation problem in particular, right? So the problems, I mean, statements right here. I mean, formal statements here. So company A has n job to be processed. Each machine must assign with exactly one job, right? So we saw this definition before. So right now, if we model that as automation problems, we are given a so-called setup time, right? Setup time is almost like a cost because we try to reduce it, right? We try to get a minimum, total setup time for this for the solution, for the job assignment, right? So in that case, the job assignment should be the ultimate solution to this automation problem. So automation turned out to be that you need to arrange this job a machine without violating any physical constraint. But the total setup time is to be minimized. So that is the objective function right here. But right now, since we intended to use binary GA, right? So the variable variable are restricted to the binary variable only. So either is 1 or 0. So in that case, we need to define our variable as a binary variable. So right now, x sub ij is our variable, our decision variable. But it turned out to be, for example, if we are dealing with a jobs problem, then how many variables we will model in this problem? So that shows, as you can see, x right now, because right now we are given the cost function, right, setup function, right, c sub ij is a two-dimensional matrix. So actually, within this matrix, there are 64, right? 64 combination. Each job versus each machine. So totally, there should be a 64 component in the C matrix, right? So similarly, we will have 64 variable. The variable is either 1 or 0, but it is not. It's freely. The definition they should be constrained because one job can be only assigned to one machine, right? So a machine can only take one job. So in that case, if your variable is x sub ij, if it is equal 1, meaning job I is assigned to machine j. So if x sub ij equal 1, that means the assignment should be that job I is assigned to machine j. So as we can see, for job, start from job 0 up to job n-1, each job can be assigned to exactly one machine. So you kind of sum up the x sub ij for I, right? Start from j up to 0, up to n-1. Only one machine will be assigned for job I. So in that case, we have this constraint equation, right? So when everything for this variable sum up should be constrained by exactly 1. So that is the equality constraint. Similarly, from the perspective of machine, only one job can be assigned to the machine. So j is the machine, right? Start from 0 up to the n-1. So totally, just one job can be assigned to machine j. So as you can see, probably you have an idea that, wow, it's so troublesome, right? Because in brute force method, we kind of just eliminate all kind of sequence, all kind of combination, right? So definitely we can find a global optima. But as you can see, once the number increase, probably when the number of job probably reach 10, even 10, it is hardly for your brute force to find the global optima because it will use up some memory, right? So it's called explosion. Dimensionality explosions problem. So when n increase, the computation complexity is kind of n factor. The complexity is n factor. So it's really big problems for computer to solve it. So only in that case, our SoftComputing or meta-user algorithm can be very useful. Solving this kind of large problem. But we are not guaranteed to get global optimized solution, right? But if your job probably is under 20, then definitely you should use linear programming method to get the global optimized solution directly. Probably maybe take 1 hour or 2 hours, but you can get the global optimized solution. It's okay. But if the number of jobs is larger than 20, then definitely, even a linear solver cannot solve it. In a certain time. So that is the place our meta-heuristic algorithm can play an important role there. All right. So this is the model. If we model our problem as a binary variable, so definitely for cases of a job, then we will have 64. We will have 64 what? We have 64 binary variable, and also we have 16 equality constraint. All right. So that is our model. But how about the objective function? Objective function is so readily. We just directly multiple each items or C sub ij and X sub ij. So the value will be to be minimized. The value should be the total setup time for this assignment, right? So we try to minimize. So the minimization problem, automation problem, turned out to be the minimization problem or binary problem. So we call it a binary automation problem, right? So that is the idea we like to have. Okay. All right. So there will be n square 0, 1 gene, right? Because we try to use binary GA to solve it. So totally, how many in each chromosome, how many genes will be assigned? N square. So remember that should be n square. To n machine wise constraint and so machine wise we have n constraint equation and n job n constraint equation too. So evaluate the violation amount. But I mean, so even though your automation problem have constraint equation, right? But if well, this problem is linear somehow. Okay, so definitely the hard computing way, anyways. For example, simplest method can keep the global optimize, I mean, within a reasonable time. So theoretically, they deal with each constraint equation and the auxiliary conversion, I mean, one by one, and they should be linear, which means that they are differentiable. So that is a requirement for hard computing. But for soft computing, for method research, we don't care. We don't care about the equation. Once the violation amount can be evaluated, then we will add that as a penalty to our auxiliary function. So we let our meta-reducer algorithm evolve somehow. So for our meta-reducer algorithm, we are not going to deal with the constraint equation at all. Instead, we calculate the amount of violation if it can be quantitativized, all right? So once the constraint can be evaluated, amount can be evaluated, then we will add that as penalty to add that amount to our auxiliary function. So in that case, we needed to model this binary linear optimization model into a genetic algorithm model. All right. So in our genetic algorithm modeling, our auxiliary function should turn out to be this way. So definitely we will have the setup total setup time, right? So C sub ij times X sub ij. All right. So this is the goal. But we kind of, because we try to minimize that value, right? So we add a positive value. If there is a constraint violation, we add that violation amount to the auxiliary function. So we let the evolution algorithm try to discard the solution who the solution have violation for a constraint violation. So by that way, so we would evaluate. You see, we just sum up because for this constraint equation, right? So the sums of the X sub ij along the row y should equal 1. So we calculate that total value minus 1. Probably the value should be 2, right? Positive. So once total is 2, then definitely minus 1 should be positive 1. But sometimes the solution turn out to be that for all X sub ij equals 0. So in 0, in that case, then we kind of short by 1 value, right? So in that case, that value should be minus 1. So we need to take the absolute value. So take the absolute value. That means deviate from exactly 1. How many deviations we have? So we take the absolute value and sum up all the machine, right here. So that is the violation count for each machine right there, and it's totally sum them up. Similarly, we have constraint, right, on the job. A job can only assign to a machine. So in that case, we look through all the excuse me, this should be the job, right? Job I violation. But this part is related to the machine. So once the sum is not equal 1, then we take the absolute values of the differences, sum up all the all the job, right? So totally we have a violation amount right here. But violation amount, I mean, very wise probably might be in different scale with your real auxiliary function, right? So since the scale is different, somehow, for example, some some automation function turned out to be money, dollar, right? But the constraint equation should be some count, right? So because the units are different or scale are different, so we need to use well, we need to special a factor, try to make them even, and also downgrade the auxiliary function. So the auxiliary function right here is what we want, right? But this part is for the constraint violation amount. So usually we'll let the user specify this penalty factor. So M is a positive number specified by the user, and you can suggest one value for the user, okay? Right. So the problem, if you want to solve it by our binary GA, we will transform this automation problem. See, automation problem has a auxiliary function, constraint equation, and restriction on the variable. Turn out to be just this one auxiliary function, okay, for our GA model. We try to minimize this bunch of equation. Hopefully, eventually, we will get a set of variable turn out to be that the violation amount equals 0, violation amount equals 0. So this factor will not turn out to be very large. So finally, we will get a reasonable and the smallest auxiliary function there. So that is the way we use our binary GA to solve this job assignment problem. And this one is very classical, all right? If later you bump into different kind of automation problem, you have a goal function, right? Which is nonlinear. It's okay, you can deal with that. And probably you have a bunch of constraint equation. Never mind. We just deal with each constraint equation as a amount of violation, and then sum them up. Try to downgrade the auxiliary function. If it is a maximization problem, then definitely we will use the minus value there. Try to downgrade it. So that is the power of so-called meta-heuristic algorithm. We can solve all kinds of problems, but we are not guaranteed the one we obtain is global optima. But definitely we will give you a settled solution within a certain time. That is the merit of the SoftComputing automation techniques. Okay, so this job assignment problem turned out to be this way. But later on, if you take a look about the chromosome, right? Chromosome actually is a series of symbol or series of number, right? But right now, our variable, in our modeling, turned out to be a two-dimensional array. Well, it's very troublesome for binary GA, right? Because binary GA, you got a parent 1, parent 2, and then you specify one point cut, and then you swap the value with the child, right? So we prefer the data structure wise should be a one-dimensional array. So one step further, we need to kind of change this modeling from two-dimensional variable structure into a list, a one-dimensional array. So it's another model right here. So remember that M is specified by the user, it's called penalty factor. All right, so the variable defined in the above equation are in matrix format, where our variable should be a list of binary variable, right? So that is our binary GA. Okay, so you need to transform somehow this two-dimensional variable into one-dimensional variable array. So that is what we want. This data structure what we want. So we will tell our solver saying that, oh, okay, right now my gene number is n squared, gene number n squared. Okay, and this one should be the constraint equation, but excluding the optimization equation. So it's a little bit, tricky. Right here, you need to specify this equation correct. So I will leave this one to you to implement this auxiliary function correct, right? So as you can see, since right now we have k, right? K is the index start from 0 up to n squared minus 1, right? Because we just have one list of variable. So how about Cij? Well, we need to know, for example, x sub k prime. What does that mean? So x sub k probably is, if you transform that from a two-dimensional array into one-dimensional, you will need to find row index, right, first, and then column index, right? So it's simple. It's not so complicated at all. You simply use the serial number k divided by n. Take an integer, right? Take integer. That should be the row index. So you will get row index right here. How about a column index? Well, take the modular operation, k modular on modulus on n, definitely you will get a residual, right? So that should be the column index. So it's not so difficult at all. So right out here. But mostly importantly is that the concern among violation evaluation, you need to carefully implement this part, all right? Because right now, for example, row-wise is okay. Row-wise is just x0, x1 up to n minus 1, right? So each segment should be a row-wise. But column-wise, you need to pick up this value and then jump to another one, the second. So you need to pay attention to the index somehow. So you need to do that by yourself. So you need to specialize this so-called solution evaluation function, right? So the result of the evaluation should be a double, right? So we try to minimize this value. So in your problem, if you are going to use your library, the problem should provide this function, evaluate the auxiliary function. So remember that we need to provide this function for our GS solver to evaluate a solution. And once we prepare this function, definitely you can directly use the GS solver to solve your problem. I mean, your job assignment problem, right? Okay, so that is the whole idea. Okay, we would like to have. Okay, so for the presentation, we will come back later, all right? Okay, so and before we solve it, I mean, using our GS solver, we might just get familiar with this problem a little bit. I mean, by using the so-called hard computing way, we try to use the simplexing method to solve it. I mean, to get some feeling anyway. I mean, for each job, definitely you are not going to bother about our GA because you can use the linear solver to get a global optimal solution. Probably within seconds you can get it. Just like our brute force, right? Our brute force definitely can solve our job problem easily, right? Okay. All right, so let us probably focus on the 8-job problem first, all right? So let me see. 8-job, okay, 8-job. So we use the notebook to open it. Let me see. Right here. Okay. So you can follow me, I mean, step by step. Okay, let us just, especially for those guys are not from IE, proper IE guys are quite familiar. So please, I mean, open your Excel. All right. So we try to use a linear solver embedded within the Excel to solve this 8-job assignment problem for us. Get some familiar with this modeling. I mean, it is an binary modeling, binary automation modeling. Okay. IE 的同学希望你们能够 follow。In case 也许你们暑假都有参加课程，那可能老师有跟你们讲过了。但是无论如何习惯一下哈。So we have a setup time right here, right? So probably I don't know. Can we do that? Copy it and paste it, right? We ask the wizard for us, right? We like to make these 64 values appear on a grid, right? But by default, it just use one cell, right? So we ask the import wizard saying that, oh, okay, not fixed. We have a separator right here, okay. Space, we use space to separate it. So 1, 2, 3, 4, 5, 6, 7, 8. Yeah, it's perfect. It's perfect. All right. So next step. General. No, we don't need it. General. Oh, probably it will be okay. Finish. All right, great. So we kind of dump the setup time into our Excel file. Is it okay? I mean, if you have a problem with using, I can show it again. So we will just want to copy the setup time here. And you can feel free to probably set, oh, okay, setup time. That should be the The first column should be machine 0, right? Machine 0, so machine 1, machine 2, machine 3, machine 4. Oops. And this one should be job 0. We always index from. And if you guys are familiar with this kind of functionality, no. It's a copy. Yeah, and I did run it. I don't want to spend too much time on that. Never mind. I just later on you can. I mean, it's just like you are adding comment there, right? So, and mark it as a color. So. And for this automation problem, we are going to use linear solve to solve it, and in particular, we use binary variable. So it is a binary automation problem. So we need to prepare our variable. So variable, well, properly just put it here. Let me put it here. 1, 1. This is just 1, 0, right? 1, 1, 1, 1, 1. I don't know whether it will work or not. Kind of. Set it all, and should I press Control key? I don't know. 2, 4, 6, 8. 2, 4, 6, 8. Fine. So kind of just means duplicate everything there. And since it's a variable, so I like to do different kind of. So this is our variable. So I just put it there. Xij. Okay. So we have Xij there. So later on, we will let the solver to get an ultimate solution for us, right? So we will ask the solver saying that, well, these places are my variable, and the variable is restricted to either 0 or 1 somehow. Okay. Okay. So this is the Xij, and remember that we have a constraint equation, right? We have a constraint equation. So we need to sum up row-wise, get a value, and minus 1. Should be equal to 0, or the sum of this line should be exactly equal 1 somehow. Anyway, either way you can model that. So we need to have the sum value or row-wise total. Okay, so we probably put it here, and this time we will write equation. This is the Mario using Excel. We can put an equation there. I mean, in this cell will update it by itself. So once I click this cell, well, I intended to compute the sum of this row here. So click on this cell and then type an equal sign, which means that you are going to enter a function, a pseudo function. So the function is definitely should be sum, right? S-U-M, sum. Once you type sum, well, actually just like a function call, put a left parenthesis. So right now you need to specify the target. And how can I specify the target? Just drag it from the start cell up to the cell. And then close it by closing parentheses. And then hit Enter key. See, so make sure the value is correct. So right now I have this cell. The value is evaluated from a function. The function is sum. The target should be B12. I see the B12 up to I12 there. So I have sum rated there, and later on we will specify constraint, right? All right, never mind. So we have this sum rated, but for the rest of the 7 row, we should do the same thing, right? So easiest way is that you kind of see that this square in the lower right. So you kind of press on Control key. Oops, not here. Excuse me. I need to read the cell definition first. So see, this is the definition, and then I leave it by enter it, so it's okay. So right now I simply click on this cell. This cell do have equation associated with it. So I press the Control key, drag it. All right, so it will automatically finish the equation specification for different row somehow. All right, so make sure it's okay, because see, click on this one, equation B12, right? How about this one, B13, right? B13. And if you want to change it, I'm saying go back to this space, click on it. As you can see, well, this is a target in blue color. It's your target. So make sure everything is all right. Okay. So we evaluate the sums of each row right here in this column, right? Okay, so we know that. So then we special a different color in order to make it distinguish. Okay, oops, not here. Okay, so similarly, we need to do what? Column-wise, characters column-wise, right? So again here, so we put an equation there, equal sum, the branches, right? Okay, target start from here up to this guy. Close it by closing parentheses. Yeah, okay, sorry. So right now we have equation special. So similarly, we need a special equation right here, right? All right, so we kind of let the Excel wizard to do that for us. So press Control key, drag it horizontally. Okay, so we need to check whether it's okay or not. So right now, this is the target. How about this guy? All right, so perfect. So everything has been calculated there. All right, similarly, I will put a color. Oops, excuse me, there. Yeah. So that is the constraint equation, right? Constraint value. So if the value is not exactly equal 1, different, we will have constraint violation. All right, so there. And how about the observed function? Observed function. All right, so I might put obj, just a comment, okay? Obj is a label, obj here. So try to put the value here. So the value should be the item-wise multiplication, right, for these two matrices, and then sum them up. So it should be right here. Should be each item-wise multiplication and then summation it, right? So in that case, I need to specify the equation. So equation should be equal what? Equal this one equal. Can I remember sum? Sum product, sum of product. Okay, this is the function called sum product. I don't know whether it's correct or not. It's a long time ago. Not long time. The last time. Okay, try to it. Correct. So it's not this sum product. Okay, so once you type sum, and then you can navigate it to product. So you hit the tab key. Similar. So, okay, so in this time I drag. It's the Cij, right? And then comma. This area. All right. Is that okay? I'm not sure for that. Okay, so let me hit enter. Try to end it. I don't know whether this is correct or not. Probably that should be correct. I don't know. Okay, so we can try that. I mean, you can test it. So if I type it, change it to 0 to see if anything changed or not. Yeah, I think it's okay. All right. So make sure you finish up to this step. So the problem definition right now is complete, right? All right. So we put a color there. So this is the objective function. We try to minimize the amount, right? Minimize this value. And definitely right now, well, you see this violation, right? It should be equal 1. This is violation, right? Violation. So you see in our method user algorithm model, we try to evaluate this guy, and then -1, saying that, wow, there's a 7 violation. The violation amount is 7. So if violation amount is large, we try to minimize it. We try to reduce it somehow in our method user algorithm. But right now, we are working on so-called hard computing method. We try to use linear solve to solve this problem. And if we have a solution, definitely that should be global ultimate solution, right? All right. So probably we should save it. Desktop, right? Job. It's okay. All right, so keep it there. So right now it's about the time we ask help from Excel. Excel do have a linear solver. Actually, it's not just linear, it's a so-called solver. The English name is solver. In Chinese, it's so-called 规划求解. This module, but the module is not by default appear, I think. So that is related to gonna be the data related to data. All right. If you cannot see anything, that means that solver is not loaded yet. Actually, it's an add-in module. Okay. So if I cannot see a solver or 规划求解, definitely your Excel has not, loaded it yet. So in that case, we go to the file menu. All right. There is option, command there. With the action command, there is add-in selection. Okay, this is the add-in selection. And then Excel try to find what kind of add-in has been registered. See, within here. So let me show it again. Excel option, add-in module. So there is a package called 规划求解, add-in. If it is you are using English version, that might be called solver. All right, so there. So okay, we kind of edit and what should we do? We will execute it, right? Execute it. Then there are 4 modules within this package. So what we want is that 规划求解, this one, solver, linear solver. Make sure. So what we have done is that we try to add, try to put in that, try to load that module into our Excel. Are you guys with me? 还是你们公共的都 OK 了？ I don't know why it takes so long. Make sure it's okay. Okay, so once it complete, then you can see there is a command there, 规划求解 there, right? So we will ask this module to solve this problem for us. So what does that mean? So we ask this guy to determine the 1 or 0 value for us, and then that should turn out to be an assignment result, right? So turn out to be the objective value is minimized. And for this problem, we know the objective minimization value should be 41, right? As you can, if you succeed in assignment 7, we remove that. So okay, so we pop out this module, solver module, right? So this guy is designed to solve your optimization problem. Okay, that is the purpose. So every automation program should has a goal. Should have either minimize or maximize or even a goal matching problem is okay. All right. So maximization, minimization, goal matching somehow, but you need to specify the objective value. It's a cell, just one cell. Okay. So right now it's highlighted, and we need to specify. Okay, this guy is my objective value. Okay. So the first and second should be the objective function, objective value there. And what kind of automation problem you are dealing with? Minimization, right? Minimize. Try to minimize this guy, minimize this value. Okay. And how about where is your variable? Right here. Specify this variable, right? So well, right now our value is in 2 dimensions. So specify this array, this metric. That is my variable. Start from B12 up to I19. This is my variable. Okay, that's it. So objective variable specify. Then we need to specify the constraint equation right here. constraint equation, right? Okay, so we add, start from here. Let me drag it a little bit. So we special our add a new one. So constraint equation specification. And then we see row wise, we start dealing with the row wise. This row value, this is value, right? This value should be exactly equal one. Right hand side can be another constraint equation, but it also can be a constant. So we simply special 1. This value should be equal 1. And well, either way, because I prefer using this interface to specify 8 constraints, so I can probably I should add a new. Yeah, once I add a new, has been added, and then another one. Second one is here. Second one, equality constraint, exactly equal 1. Another one, third one, exactly equal 1. Added. This guy equal 1. Added. Fourth one. Oh, it's kind of confusing. Fifth one, 1. Added. This one equal 1. Added. This one equal added. Last row equal 1. Added. Okay, cancel it. So let us see. See, K12. This is K12, right? Oops, excuse me. I kind of change it so because it's focused, so I need to change it, turn it back. Make sure it is not happening here. Okay, so 12, 13, 14, 16, 18. That's okay. So it's a row-wise constraint, right? But we have another constraint, right? So we need to add again column-wise. This guy is exactly equal 1. Edit. This one, second one, third one, fourth, fifth, sixth, 7, 8. Okay, so we have totally should be the 16 constraint equations, right? So 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. So we are almost there. But finally, we need to let the solver knowing that our variable value is restricted to binary, right? So we add another one. Okay, this 18th constraint equation, right? So we add another one. What should I do? Yeah. Yes, add and select all these variables. So all these variables, they are restricted to binary. See, there's a bin binary there. So we tell the solver, well, these variables are binary value. Okay. And we need to add it, cancel. All right, so these are our constraint equation. Our variable restricted to either 0 or 1, and then the rest of them are the constraint equation. So far, the modeling wise is complete right now. And since our problem is a linear optimization problem, so you had better choose the ORG Simplice LP linear programming model. So make sure everything is right. Okay, this guy, right? Variable. Okay. So once everything is ready, then you hit the solve it, the button. Okay, so optimized solution has been found somehow. Well, if you like, you can look into the detailed information there. As you can see, this is the linear solve, the solution solved for us. See, so turn out to be that each row, see, each row value should be exactly equal 1. So that is the global solution for this job assignment. So it's really quick. I mean, definitely, we for IE students, they learn this method in the very beginning, probably from the software study. That is the meta. That's the hard computing's way. But if you switch to do that, the problem should be linear. Actual problem should be linear. Constraint should be linear, and it can be solved directly. It's quite fast, right? So that is global solution. So similar right now, in our GSO, we try to prepare a list of 0, 1 variables as our chromosome, right? And then we need to ask the GSO, try to do the crossover and mutation operation, and eventually, hopefully, we will get a list of 0, 1 that does not violate any constraint violation. And then also, the objective value is minimized. As close to global optima as close as possible. Right, that is the purpose. Okay, so we take a break, and then later on we will back to our GS solver. I mean, if you still have a problem, you can leave there, and then I will help you. Anyway, all right, we take a break. So, okay, once we have a little bit study about the hard computing way, right? So we have a constraint equation, and then we can use the linear solver. So actually, for this job assignment problem, if the scale is small, I mean, probably the number of jobs is less than 20, definitely, usually use linear solver to get the global optimal solution directly, right? Don't bother about GF, about any meta-heuristic algorithm. If your problem is a small problem, if your problem, in particular, if your problem is linear, definitely you should not use genetic solver to solve it. Okay. All right. So let us go back to our system. Okay. So I will use the work. Oh, mischance. Oh, right here. I need to do that. So let me check about what kind of progress she has achieved, all right? So we I better prepare a library on the desktop. It's much easier for me to locate it. All right, so okay, please, I mean, replace this image, I mean, with a meaningful one, okay? I don't know, it's a photo, it's not an open, it's not related to open. Try to find, I mean, in the internet, you can find a lot of icon file for open, all right? So, open benchmark, then so we have desktop. Job assignment libraries. How about the 8 jobs problem? All right, so well, let me check about later on amazing whole solution. Okay, I do check your assignment 7. I'm not going to grade it anyway. Some of you, I mean, once you run the 8 job, well, it looks like it's stuck up, right? Well, if you want to display the details, somehow I mean, there's no solution came out, all right? The problem is, you have the same problem, right? So, get all solution or high detail. All right, if I check it out, it's okay. I mean, is it finishing? No. You see, I mean, some of you have this kind of similar phenomena. The problem is that because you are using okay, pay attention to that. You are using rich text box. Rich text box deal with all the contents as a text, as a string. And if you keep updating the string, it will use up a lot of memory. So it turns out that nothing is complete somehow. All right. So this computer is okay. I mean, let me check it out. 那个罗军。You are using this is the text box. It's rich text box. So if you guys are using rich text box, when you run the AJAB problem, probably you will not see anything come out because the applications look hung up there, right? 对不对？都没有人对 yes， 还是你们都不知道你们做了什么？八个叫我 run 进去 run 不出来，举手一下。都有 run 出来才怪，老师已经看了几个人都没有 run 出来，要等好久。没有啊，8个叫你要显示才大概个16秒。对，那16秒啊，其他同学呢不同意，对不对？我的怎么进去都没有出来，对吧？有人没有出来哈。好 ，problem 是你的 display 哈，因为我们要 show display all kind of detail, right? If you are using rich text box to display your detail, definitely it will look somehow hung up there. Nothing came out. The problem is that if you are using rich text box, actually these parts are actually a text. It's a text. So in this case, that means you need to use another control. Okay. Let me show you. I mean, 罗军用的这个是你用的是 rich text box 嘛？我们等一下 check 一下。你看啊 ，for example 哈。If we open a benchmark and AJAB, open it, we are not going to hide detail. We don't like to show detail. And usually, probably it will take at most 20 seconds to complete it. Because your computer is so slow. If in that case, it probably take 20 seconds will be complete. You see, so far there is nothing reported yet. This problem is because you keep updating the user interface, and the user interface take a lot of memory operation there. So that drag your speed, drag your computational flow. So you will wait probably 1 or 2 minutes and finally get it. It's not normal. Okay, so if you have this kind of problem, try to okay, it's done right now. So probably you take maybe 40, 30 seconds. It's not correct. It's not okay. It's not okay. All right. So in this case, you need to change it into what? You need to change the user interface from using the rich text box into a so-called list box. 注意听哈，就是说，我不知道老师上次 demo 是告诉你是用 rich text box or list box. You should use list box if your contents will contain a bunch of information. You are not going to use rich text box. So that is why your speed is so slow. Okay. So right now, these students use what is a rich text box. All right. Name is called what? Rich text box solution. Right. I copy it. I delete it. Okay, I deleted it. I tried to change it into the ones called list box. List box. Instead, I use list box. The coding wise will be a little bit different anyway. So right now I anchor this control because it's the mostly important control. It should contain as many information as possible, and then I replace the name exactly into the same name, rich text box solution. Okay, and if I try to combine, definitely the syntax error will come out. Never mind. So right now, where I'm using a list box to show the detailed information, so I need to change the seamless part there. So the first one, deal with the first one. There's no need clear anymore, right? But instead, list box. So right now, rich text box, actually, I changed the variable name right here using the replace. 重新命名哈 replace. I changed it where it's a list. LSB. It's a list box. LSB output. So my LSB output is the list box, not a rich text box. So I don't have clear function. Instead, I have items collection. Items collection clear all clear all item. Anyway, it's a collection. All right. So I kind of deal in with the first problem. Second problem is right here. I don't have a dependent text. You see. So originally, if you're using rich text files, actually you kind of change the text or that rich text files somehow, and that is really costly because you are dealing with string. Later on, I will show you this example. Anyway, so I have a string want to show out, right? So what I need is instead I ask the items add another string here, right? So I will do the same modification right here. This part. So another one right here. I don't have appended text. Instead, I use items add another item. And in fact, the item is a string anyway. Oops, excuse me. Repeat oh, okay. Put that items add. The name is not complete, so I rename it again. So let the Visual Studio do that for you. Do the name change for you. LSB output. So last one here. It's already clear. So simply just ask items clear. So let's see the differences. Okay. Open benchmark, a job. Show all detail, get all solution. Okay, it's done. 20, well, it's reasonable. I mean, it's 20, 25. I mean, it depends on the speed of your computer. So it is a settable. So right now we simply add an item. An item just a string. So the string is fixed somehow. It's fixed. It's quite different. I mean, rich text files is the whole thing is a string. And why if you are using the rich files is taking so long, and then it might use up the memory. Okay. You can check that once you run debug mode. If you are using, well, I should show you. I mean, before I change it. Okay, you will see that I mean the memory has been keep using up, and then garbage collector came out. Garbage collector came out. I mean that will slow down your computing speed. Okay, so the reason is that I mean string in C# is a so-called reference type. And all the content has been allocated on heap memory. And once you add a string, then definitely that will take up memories in the heap. So if you keep updating your string, then a lot of scrap or fragment string will be allocated on the heap, and eventually you use up all the memory. So garbage collector came out, try to clean up the memory for you. Okay, so I mean, I'm going to show you is that what really happens once you have a string add another string. I will show you one example. In C#, if you are going to deal with the string and frequently, you need to pay attention to this problem. It is not suggested that you use, for example, string NTU, right, plus ME. Usually we should have this string. We might call string INGS equal this one, right? So usually we might have a for loop, try to add one. For example, if you have, if a vector proper 1.234, right, and 2.4, 3.5, 6.7, etc. And you try to write the contents out. So you have a string s initially equal 0. Then you have for loop for each suppose it's float f in v, right? So v is a vector, it's one dimensional vector. So in that case, so for each float f in v, then s equal s plus f, right? So probably f to string. So this is the usual way you program it. For a small dimension vector is okay, but probably your vector size might be very large, probably 1,000, 10,000, right? So in that case, if you have 1,000 items, then this statement will be executed 1,000 times, right? Well, it thinks, well, that's okay because we just let the computer do that. But the problem is that if you are using this operation, this 1,000 times will use up a lot of memory in order to dealing with the final string. Okay, so initially, if s equal assigned to none, right? So s, right? For example, memory use is like s right here, s string, right? So there is a memory, and since string is a reference type, so actually for this s, it takes about 4 bytes. What is 4 bytes? 4 bytes try to record a memory address. What it contains just a memory address there. So initially, for example, probably you say v, you might put a v there. V, so s initialization is with v string. So once computer executes this to this line, computer will use heap memory. Suppose the heap memory is right here. Current location, current usable pointer is right here. Oh, okay, you have v, right? V string. So you will allocate memory, put v there. Suppose the heap memory probably is 111. So right now you keep 111 there. So your s can access its contents by referring to this address 11 right now is v. So currently s is v. And then for the first time, s equal s plus 1, the first element, right? First element 1.34. So right now you will tell me v 134, right? So what do you have? This string sum v sum f, excuse me, right here. The first f should be 1.35, right? So 1. So right now this new string so v 1.34. So in that case, you have new evaluation result, right? S plus f to string. So in that case, computer will allocate another string memory there. So this part is v 1.345. As you can see, this is 1, 2, 3, 4, 5, 6, 7. There were 7 characters allocated on heap. And then start from here, probably the address is 115, right? 15. So computer update this address for you, 115. So right now, your string up to this point is v 1.345. So for the second item there, you again execute this line s equal f to string added in up. So you have v 1.4, 2.4 whole string there. Try to reassign back to string. What computer has done? Oh, computer keep using heap memory. Keep using heap. Right now v 1.345, 2.4. So this chunk of memory have been again allocated. So if the starting address should be 125. So right now it changed into 125. So right now your s current is equal v 1.345, 2.4. And then 3.5. So again, after evaluation 1.34, 2.4, 3.5, the whole string again allocate new string memory there. So as you can see, the heap memory will be used up quickly. So in that case, once heap memory is not enough, then the garbage collector will come out. So that will slow down your computation. So pay attention to the string concatenation carefully. So in that case, what should we do? Well, if you look into the Google, try to search internet, take a look about this problem. It will suggest you to use a class, this class is called String Builder. All right. So that is the problem if you are using rich text box file. Try to append a lot of text there. You will kind of use up all the heap memory, and the garbage collector came out. You can see, once you execute it, you can check the progress. For example, right now I think I should have the original version for you to take a look at. Show detail. So during the debug, you can check the progress. Okay, see, once the yellow tag came out, that means the garbage collector executed. The platform try to do something for you, try to clean up the memory for you. So you can see the memory using is keep increasing, but it's okay. Since right now we're dealing with the this part, so it's okay. So up to this point, we have a garbage collector. I'll see it's done right now, so it's okay. So if you are using rich text, you can see, well, the garbage collector keep coming out, and then it slow down your computing speed. So in case you like to add up a lot of strings step by step, what kind of help you should ask? You should ask the so-called string builder. There is a class called string builder. String builder. You need to instantiate first new string builder. And string builder have a clear, because the idea is that string builder is a class. This class has already allocated a chunk of memory. For your string manipulation. So all the string manipulation will be done within this object. If the space is not enough, then the string builder will allocate another chunk of memory. So if you are going to repeatedly append a lot of string, you should not use plus. You should not use operator plus. You should ask the string builder help you. So we will use string builder. The string builder append text somehow, and at the end, you simply ask SB to string to print out the whole string. The whole idea is that string builder have a scratch of memory there, and if the content does not exceed the size, definitely it will not allocate new memory there, right? Okay, so that is the issue. For some of you, if you use the rich text box to display the result, the detailed result, you might see that you cannot complete the 8 job problem in times once you turn on the detailed display. Okay, all right. So this is another knowledge you need to know. Okay, so let me check the functionality of binary GA. Okay, so we open a job problem, and then this time we try to use GA to solve it. So for assignment 8, actually I think you can complete the 01 binary GA solver, but probably you have not completed. I will see what's going on with your project. So create a binary GA first, right? So as you can see, all the common property will show up right here. Particular GA solver will have their own property, so it's okay. So crossover cut is 1, crossover rate, iteration limit, ratio, mutation rate of 20, minimization problem, right? But usually we will not let the users change into the maximization, right? Well, it's once you read in the particular automation problem, definitely not either way is the maximization problem or minimization problem. So we are not going to let the user arbitrarily change it. So you should better hide it or make it non-browsable. Deterministic model, we might prefer stochastic. So we let the user choose it. And after the user reset the parameter, then we need to reset everything, right? Probably he might need I will instantiate 50 chromosomes somehow there. So only once the user has finished the setting, then we need to reset it. Okay, and okay, so at least we will see the progress or the solution evolution, iteration by iteration. So usually we have one iteration, check everything out. It's good. I mean, you see, right now our chromosome is a one-dimensional array, right? But it's much more meaningful. I mean, once you display that as a two-dimensional array, see, what we expect that just one in each row, right? Just one in each row, just one in each column. So right now, constraint variation, see 30. Okay, we can evaluate. So our objective variable, remember that not just the setup time. You need to add up the violation amount times this penalty value. We try to downgrade the objective value. So eventually, after the solution evolution, hopefully we will have final solution satisfies all constraint equation. That is the beauty of meta-heuristic algorithm. We are not dealing with the constraint equation directly. So we are not asking that the constraint equation should be differentiable or it should be linear. No, there is no any restriction on constraint equation on objective function. No, our meta-heuristic algorithm can solve all kind of optimization problem. That is the beauty. That is the merit of meta-heuristic algorithm. Remember that. How can we do that? Well, we just add a penalty to our objective function in case there is any violation. And the violation should be major in value anyway. So that is the this is the first solution, right? First generation. The best solution so far right now is in this way, and the objective value is still high, pretty high, right? Because the penalty has been separated the amount into large differences. So value is still high. So second iteration, third iteration, see. So well, it's kind of weird. 1,000, right? Yeah, okay. That should be keep reducing. Remember that only solution is improved in each generation. Then we replace the best solution so on. So the best solution should be always the best one. Okay, it should be lowest one. All right. So right now, the constraint amount has been reduced to 8. So 800, right? See, 970. There is an 800 value that is dragged down by this constraint violation, right? So let us run it to the end. So the end condition should be the iteration count reach the limit. All right. So, well, graphics wise will be a little bit late somehow. So in this case, that means once you look into the progress, that means that your solution has been well converged. All the population probably will converge to the same solution. So there is no improvement there. So you still can regard that as a local minima somehow, right? So we have a feasible solution, right? We do not have any constraint violation, but the objective is not global optima. We know that, and we are not going to claim that our solution should be the global optima. What we say is that the solution we obtain is close to optima anyway somehow. So as you can see, your solution can evolve from violating a lot of constraint equation eventually step by step and into the one without any constraint violation. That is the beauty of evolution algorithm. So remember that. So you need to have your GS solver reach to this point. Okay. So and then so usually people might change the factor. For example, I might change the mutation rate, try to make it much more higher. So probably I use 0.1, and I might reduce the crossover factor. So remember that for soft computing, a lot of parameters are provided. So for the user, try to tune the methodology in order to get the best one. Even those nowadays the so-called deep learning method, right? Again, there are still a lot of options, a lot of parameters should be tuned by the user. So once I change everything, I reset everything is ready to run to the end. So this time I obtain another solution, which is also a feasible solution, but the objective value is better than before, right? Okay. But again, I mean, it's kind of hard. I mean, for the binary GA to reach the global optima, right? Because the problem, original problem is so small. But right now we kind of augment it in order to use the binary optimization model, right? Definitely, for this problem we should have a variable, right? But right now we have turned out the model turned out to be a 64 variable and introduce a bunch of 16 constraint equation. So we kind of augment our automation problem into a very complicated one. So since it's a complicated one, you are not going to ask the matrix user algorithm to get the global optima for you so quick. No, it's nearly impossible anyway. But if you keep running it and you keep changing some parameter, probably it's also likely that you can get the global optima too. All right. So this 132, although the control variation is okay, and sometimes even you change the penalty factor might influence your computation result. Okay, so you guys, that is why it's very important. The user's interface is very important for SoftComputing. We will let the user arbitrarily change this phase. So right now I try to reduce the constraint variation penalty. Turned out to be 50, right? So I kind of reset it. Try to see whether the solution will improve or not. So right now we can easily get a solution without any variation, right? But the still high, okay? Okay, it's done. So probably I don't need to spend so much iteration there. This time I change the selection into stochastic. I don't know whether these students has completely, successfully implemented stochastic selection or not. You need to do that. Take a look at the slide. Try to implement that. Try to simulate the rate wheel spinning. All right, to select the chromosome for the next generation. So the solution might, if you are using stochastic solution, then definitely the same chromosome probably might be selected multiple times. It's okay. It's normal. It's another way for the GA to select, okay, chromosome to survive to the next generation. That is the standard way, right? So we will let the user choose it. If the user prefers stochastic, then definitely the user can use that. If the user prefers deterministic, then definitely they can test it. So we provide all kind of options for the user to try to do that. So if you are using stochastic method, so in that case, you see, iteration best should not be as skewed by the so far the best. So remember that. You see, we have iteration best line shown up. It's different from the so far the best. All right. So in general, you see, once this termination condition met, we still have violated the constraint variation for stochastic solution, right? Well, it's normal somehow. For this job assignment problem, so probably we can conclude that stochastic is inferior to the deterministic selection. But it's not true for all automation problems. It's definitely problem dependent. Okay. Okay. So what else I can do? Well, I might just if I stick on stochastic selection, if I change the penalty into 120, let's see what will turn out. We still have constraint variation, right? 6. It is not reduced to a feasible solution, okay? So how about change it into it? So you should, if you want to study the intrinsic property or that automation problem, you should keep changing the available parameter, to see the behavior of your automation solver, right? Now, it's not good at all, right? So we are still, I can change that to 200 population, so to a larger population, right? So since the population is large right now, so each iteration will take much more time than the previous one. Well, it seems that stochastic solution is not promising, right? Comparing with the deterministic. So fine, we can change it. All right, see, this is a global solution, right? Bingo, we got it somehow. Well, so I change a high, I use a high penalty factor and use deterministic, and I employ 500 chromosomes to do that. Well, I reached to 41. See, it's a global optima, right? You can reset, try to get it again. It's not always happen, right? Don't expect that. It is not hard computing way. So since it's so computing way, so we kind of use another random number to carry out the stochastic processing. Okay, so I think for these students, the binary GA is done. It's completely done. And when I did not mention, I mentioned in last assignment, is that how will you implement that? So right now, see, right now in your project, your GA solver has been independently developed in the project, right? So our GA solver there, right? So it's our GA solver. We try to populate it somehow. If you are interested in it, later you can implement a real number encoded GA by yourself, all right? So I'm not going to set up another project for you. So you can make your library complete. So binary GA, right? Binary GA. So binary GA is ready. Since we are using object-oriented design, so actually, once you complete the permutation GA, generic binary, okay, she has not studied the permutation GA yet. So binary GA, okay, last time, constructor, right? Constructor. So what constructor asks is simple, number of variable, which it will be used to set up the number of gene. Automation type, maximization, minimization, or goal matching. Anyway, the most important thing should be the objective function, pointer, or delegate. I mean, in C# we call it delegate. So delegate is in fact, it's a pointer. I mean, in C programming language terminology, that should be the function pointer, point to a function. But in C# we call it a delegate. So delegate will bind with a function. The function type is specified by the delegate and somehow. So we design an objective function delegate. It's a temporary function. It's temporary function. So right now it's a byte base, right? So base, that is what we have done before. So initially I will override it initially because each derived GA should initiate their chromosome by themselves, right? Because they know the type exactly. So that job should be done in the derived class. So okay, crossover card. Okay, so we need to implement this kind. Override, generate a pair of crossover children, right? Permutation wise, we binary is a little bit different, so we did it in that way. So how can we use it? In your application, right? In your application, our application is we try to use that to solve our job assignment problem, right? So before we instantiate and binary GA, right here. So last time I think we have prepared a function, right? If I can remember, we will prepare a function for the GA to call it to evaluate the objective function, right? So binary call right here, right? So this function, because right now our application will ask binary GA and permutation GA to solve our problem, right? So we need to prepare this function. See, the binary GA asks a function, right? In the constructor, ask an objective function evaluation function. They ask this function. So that is delegate objective function. Basically, that is the function take the byte array, and then you should return it. So you will take byte array and return objective value back to the caller. The caller should be the GA solver. So it's related to our problem right now, right? So our problem tells that, well, so see, create binary GA quick. So we knew a binary GA, right? Oh, okay, since the binary GA asks for the number of gene, right? So our number of variables should be number of job times number of job, 64, binary, right? 0, 1. Now the dimension type is minimization. And I prepare this function for you, binary coded setup time. So that's it. So what a GA solver asks is number of gene eventually. So number time the job, automation type, and the function delegate. The function delegate. That's it. So the function delegate needs to be follow the specification or the constructor. So this is our solution. So if the user, the user is the GA solver, prepare a solution, equal solution for us. So actually, well, this solution is actually the chromosome, right? So we still can remember that as a CHR chromosome. But in fact, for the application, it's a solution. So right now, GA has prepared a solution. Solution is in byte array. It's my responsibility because I am the problem itself. I need to evaluate this solution and send back a value back to the GA solver. So GA solver have a value, objective value, for the solution. So later on, GA will do their evolution operation there. So see, so we need to get objective value, right? So this part definitely we need a solution time setup time, right? So right now solution is a list. Remember that it's a list. So we need to identify the row and column-wise stuff there. I don't know. Well, time job, right? Okay. So identify the it's start from the setup time, right? Setup time, job I assigned to the machine J. So you need to locate the variable there, the variable. If it is 1, then definitely we have amount there. If it is 0, then we do not have it, right? So for the first part, well, it's simple, just objective, just setup time. But we needed to evaluate constraint violation right here, constraint violation. So she has evaluated constraint violation, right? So minimization, well, objective value add up, constraint count, right? See, so Ms. Lin prepare another function. We call it helping function. For this solution, try to evaluate the constraint violation there. So you see, it's quantized somehow. The violation will be quantized, have value associated with that constraint violation. So we have constraint violation came up, and then we time the penalty factor there. Well, that's perfect. Convert into double, right? It's a penalty specified by the user from the user interface. All right, so we downgrade objective value, right? Since it's a minimization problem, so we downgrade it. So actually, it means right now it's our application, right? So we don't need to use this part. We don't need to do it because we know definitely our problem is a minimization problem. So we can simply use return objective plus add up this constraint violation amount times the penalty factor there. So your objective function should calculate the really objective value and also the penalty part of the constraint violation amount. All right, so that is the function you need to prepare. That's it. So for the binary GA, you need to exercise that by completing this function anyway. And if you, for this today is good. Because we are dealing with the assignment problem, right? So in the user interface, she did a very pretty job. See, all right. So you see the penalty amount factor is here. So we create a binary job, then create a binary solver, and then once you run it, you see she has shown up the current basic solution right here in the matrix form. So we can look into this solution directly, knowing that well how many constraint violation has still there. So you see, since she has that function, so she can report this amount, constraint violation amount, for the viewer, for our user, to see this problem, to see the progress of this solution, have much more information for us. Okay, so that's good. That's good. That's really good for this work. Okay. So is there any problem about the job assignment problem using the binary GA? Okay, you need to do that in that way. I don't know whether you implement this guy or not. Usually the traditional way is just one cut, right? So if you use a special tool where your code really carry out 2 cuts, crossover, you need to do that. I think the implementation is not so difficult at all. Okay, so for each cut, it's definitely stochastically determine the cut position. So each time the position should be changed, right? But right now, if I use a special toolkit, and definitely you will randomly assign two position, and then try to solve the position. And the first part swap, second part does not, third part swap. So it still can be done easily anyway. Okay. All right. Is there any other question about the first part? We need to use our GA binary GA. Our binary GA is almost done in assignment 8, right? So what do you need to apply that by completing this function, this objective evaluation function, and then you need to look into this equation right here, this equation. So that is the setup time, right? This part is the penalty count add up by the factor, penalty factor. Downgrade. We try to downgrade the objective value, and then through the evolution algorithm, the solution will evolve to the one without any constraint violation. Right? Okay, so another important job is that we try to use our genetic GA, try to create our permutation encoded GA. Alright, so that's another property. So in this case, it's so rarely, and if you complete the permutation GA solver, then I still ask you to solve the assignment problem, use permutation GA. So that will be readily encoded. Anyway, there should be no any constraint violation. And your observable function, because right now permutation wise, you see the coding, the chromosome should be well n gene, right? N job should be a gene. And since we are using permutation, so it's okay, just the value start from 0 up to n-1, so just permutate. So the objective function evaluation is so simple, right? C, you see, C x sub j, just sum it up. So x sub j is meaning that, well, which job, x sub j is a job assigned to machine j. So for example, if x1 equal 5, okay, x1 equal 5, meaning what? Meaning job 5 is assigned to machine j, machine 1, right? So it's very simple. For this function, it's very simple. Once you have completed permutation, I have a function prepared there, right? Permutation called the setup time. Again, you get a solution. But right now, solution is a list of int, right? Right. So this function is designed for permutation GA to solve our problem. Okay. So the first one is a byte array, right? Byte array is this function is will be used for the binary solver. This one will be used for the permutation GA, and the permutation is quite simple. It's much more easier than the binary coded setup, right? Okay, so you need to do that by yourself. Once you complete the permutation GA, try to solve it. What you need to do is just complete this objective function evaluation. That's it. It's very simple. So the problem is that we need to augment. We need to enhance our GA solver, right? So since you have a very well designed genetic GA, so right now it's very simple. Just like the fuzzy set, right? We have a fuzzy set base class designed, and then new fuzzy set will be derived quickly anyway. All right, so we will go back to our GA solver, right? So we try to extend the functionality of our GA solver. So we add another classes. So we call it binary GA, right? So this time we call it permutation GA. Permutation GA. So if you are not familiar with how should we do it, well, we can just show the binary GA as an example, right? Where everything should be similar, right? So we put it here. And then this is the one we like to add. Put in another right-hand side. So it's just comparison. All right. So we need to inherit, right? Inherit from where? From generic GA, right? And since our generic GA is a temporary class, right? So you see, binary GA inherit from the, and remember that the class should be declared as public. Otherwise, the other package cannot use it. So we need to declare as this is public. So other project can directly instantiate the class of this permutation GA. So inherit from generic GA. And the data type wise binary because it's just 1 0, right? So we use the byte. So inherit is a colon G E or C. The intelligent highlight display for you. So hit tab key, left angle. What kind of data type you are going to have? Definitely that should be int. Or in particular, you can use unsigned int. Fine, it's an int, right? So we clean that our permutation inherit from this GA. And once you finish this declaration, you see red query light came out. The reason is that your generic GA does not have a default constructor. Your parent has a specific constructor. So since you are a child class, you need to prepare a constructor, invoke one constructor of your parent. So right now, Recurrent came out. See, take a look. You see, you did not provide any such kind of thing because the generic GA needed this information. And most of them you can directly copy. I mean, from binary GA. See, binary GA. See, this guy just pass to the parent. So because the parent need a number of variable, problem type, algebra type, blah, blah, this kind of thing. So it's very simple. Oh, okay. So I take advantage of the old code. I try to copy it, but remember that copy always have. Well, let's keep it wrong. All right. So I copy it right here. Change the constructor name into this class name. Okay, but objective function is not byte, right? So I need to change it int. So I'm asking that user should provide a function. That function take one argument. The argument is the int array, and the return double to me. So objective function delegate should be int. All right, so everything, the rest of them should be the same. So number of variables. See, so we have complete the constructor permutation GA. All right, so once we have this guy ready, right? For example, so let us compile everything, right? To make sure so far compilation is okay. So review all the solution, including 2 projects. Is it done? And see it. Okay, 2 successful. All right, so everything has been updated. So right now, you see this is constructor. So similarly, I'm using data in your main form. If you want to invoke permutation GA solver to solve it, then probably that should be in this permutation GA, right? GA. Okay, this button is already there. So let me check whether it is implemented or not. Nothing has been verified. So see, it will be similar to the binary GA. So initially we have binary GA where binary. See, there's a binary GA solver, right? So similarly, well, actually, we don't need to have a each individual object anyway. We can always call that a generic, but since right now the generic GA is a temporary class, so we still prefer permutation GA. Yeah, permutation GA ready, right? Not just solver. It's duplicate, so P solver. Okay, P solver. So the first thing is that's still the same. P solver equal new. Invoke constructor, right? Permutation GA. Number of variable, right? Is similar, quite similar to the permutation GA. So let me hide it. See, almost there. Number of job, blah, 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 blah. The same. Because only you know the number of job, right? So number of job time. No, I'm not going to augment our problem. Just number of job. See, it's a permutation, right? Then you go there. So how about a problem type? Okay, type of space key. IntelliSense will show up. Emulation. This emulation is designed by you, right? So it's a minimization problem. How about the third one? So the third one, you should specify your function here. This function is called, finally called the permutation coded step time right here. This function name is not perfect. It was not so good at all. Okay. Fine, that's okay. So permutation coded step time. So we let the solver knowing that once the solver want to evaluate encoded chromosome, they should invoke this function. And then I'm an application, I will return an objective value back to the GA solver. So that GA do their job. And what I need to do is just prepare this solution evaluation function. That's it. So for the user, it's very easy. So later on, if you have another new problem, okay, you should set up another project and then invoke the your library. Okay. Remember that what you are now doing is very powerful. You can have your own optimization solver. So later on, if you have different kind of problem, for example, in mechanical design, you have design optimization problem, and you use it set up your problem and invoke your GS solver, you can solve it, okay, in a similar way. Okay, I think it's about the time we take a break. So why not you just keep doing the rest of things? So well, we'll just take a break and then we'll be back to see what kind of function we should override for the permutation GA. But mostly, the similar GA operation has been done in the generic solver. So it will pretty easier for us, but it's not so easy anyway because we have a bunch of different kind of crossover we need to implement it. All right, so let us go back after the break. All right, so let us continue with our permutation GA. All right, so constructor is ready, right? Permutation GA. GA. So each constructor should dealing with their own requirement. But so permutation right now is okay, but we will have what? We will have our crossover, right? See the crossover right here for the binary GA is so simple. It's simply override. Okay, initialization should be done first. And for the binary GA, there has a property called number cuts, right? In composition there. Crossover cut. All right, so that is the particular property, right? But for now, for our permutation GA, it's okay. It's restricted to 2-point cut, right? 2-point cut for crossover by default. But later, if you think about if property user might have 1,000 gene, in that case, you simply use 2-point cut for crossover. Probably is not the best way. So later on, you can somehow extend it. But so far, our permutation GA probably just restrict to 2-point cut. So only the middle segment will be interchanged. Okay, so it's the easiest crossover anyway. But for the crossover, we need to prepare an enumeration, right? Because we have, I think from the slide, we might have 5 or 6 crossover standard. We call it canonical operator, permutation operator. So we need to implement that by ourselves. So I have asked you guys to do something in advance. Later I will show you. So for this moment, let us deal with the initialization first. Okay, dealing with the initialization first. Initialize population, so we need to override it. So basically, you directly dealing with all the chromosomes from the zeros up to the population size. See, similar. So well, we can copy and paste, but we prefer maybe we start from the keyword override there to see how many functions can be overridden from the generic GA. See, all these functions we have prepared as a virtual function, right? Generate and mutated children all perform mutation operation, right? Either way, because in the binary we kind of override perform mutation, but right now it's much easier for us to perform so-called chromosome-based mutation. So we will override this one later, crossover later, and initialize. So right now we are about to start with initial population. So once the instance is highlight this function, you simply hit tab key twice. So override initialization. Well, I can simply copy, right? Copy everything from binary, but definitely we need to change it. So row-wise from 0 up to population size, then we need to assign chromosome, right? And definitely that will violate the constraint, right? It is not 0, 1. So, well, start from C, number of gene, right? Similar. So probably because it's permutation, so we might set into C. So all the chromosomes start from C. C, the value should be equal to get C. So we need to shuffle it, right? Because it's a permutation, right? So initialization should be not always start from 0, 1, 2, 3 up to the n minus 1. So we need to shuffle it. So we will prepare a helping function. Usually that should be private. We are not opening it to other classes call it. So we call it helping function. And I think we probably can copy something from the generic helping function. Shuffle. Where do I implement shuffle? I think last time we have shuffle there somewhere, right? Generic. Yeah, right. In generic GA, we do have shuffle function, right? But that is an array shuffle. If I can remember correctly, we have shuffle function. Yeah, shuffle integer array. See, we have this function in the parent, right? Generic GA. So you give it an array, and then specify the length. This function help us. Initially, I mean, regularly start from 0 up to length, right? And then shuffle. See, this is randomly shuffle. So we can directly use that. So this time, well, it declared accessibility protected. So we can keep using the one inherited from parent. We do not need to prevent another one in the child class. Shuffle integer array. Give it an array, and it will return a new array back. It will try to shuffle the item between them for us. All right, so let's back to our permutation GA. Chromosome C should assign a value, right? It's an integer, right? It's an integer array. So R wise lemon is an array. So this is an array. It's a two-dimensional array. So we can ask that shuffle integer array. After this guy help us. Okay, I put this array for you, and I tell you the length should be number of gene. So we set one helping function by calling the one has been set specified in the parent class. So that's the beauty. So I give this array to you, and then this function will initialize each item start from 0 up to length minus 1, right? And then try to change it, shuffle it. Is there any question? Shuffle try to rearrange the order, right? All these items somehow. So we keep using that. It's very important. I mean, in some cases you need to have this function. Oh, it's done. Right now it's done. Initialize population is done. Okay. So what kind of function we should have? As we can see, we try to implement another one. So helping function is not required. So this part should be the overwritten function. So another override function. What? Generate a pair See, a crossover children, right? So we know the index, parent 1, parent 2, we are about to create child, put into the C1 and C2 somehow there. So we need to implement this function by our own. Right, but if you take a look at the slide, right, for the permutation GA, we have a bunch of crossover. So definitely we will have a property that the user specify the crossover. So I'm not going to cover everything, all right? So for mutation too, I mean, you need to design the enumeration of mutation. So let us go back to enumeration file, enumeration, right? So we put all the enumeration right here. So we have previously we have automation type, we have GA type, and we have delegate, right? It's a temporary function. It's beautiful. We can say that it's a high level object-oriented technology, technique, use temporary class. So we could declare another one, public, new. We call it permutation crossover. OPERATOR, operator. Permutation crossover operator. Even though it's lengthy, it's okay. We prefer that. So you can PMX is meaningless at all, right? All right, so we just partial map crossover because we know it's a permutation called partial map. Order this. I cannot remember the rest of them. You needed to implement them one by one. Okay? Partially map, orders, and properties, and I cannot remember exact positions, etc. I think at least there should be five crossover. So similarly, you need to complete the enumeration definition about mutation operator by yourself, okay? So remember that permutation have individual, different kind of permutation, different kind of crossover. So we need to, I hope you guys implement all of them to make your GA library complete. But you need to spend a little more time on designing the computational procedure. Okay, so permutation crossover. So back to our permutation GA. So right now we have a public property. It's called permutation GA crossover. We call it crossover OPERATOR, crossover operate. Set, get. It's a shortened way. If you do not have a data field associated with this property, it's very simple. So itself will be the variable anyway. You can set and get and set the initial value. It's enumeration, right? That partially map, partially map. So generic permutation GA have a property for the user to select it. And similarly, you should do that similar for the mutation operator, all right? So we're going to do that by then. So, and then to go back to the generate a pair or crossover children. So we need to switch crossover operator. It's an enumeration, right? Enumeration is an integer type, so it's okay. Case, partially map, break, case, orders, break. Prepare the skeleton for this coding anyway. So it's about the time you implement the partially map crossover. So you need to guarantee that the children is legal, generated are legal, okay? So every integer appear exactly only once in the chromosome. So that is the responsibility. And then go back to the instruction list in the first part. All right, so pay attention to here. I will ask you write the pseudo code first, because from previous experience, I kind of knowing that a lot of students did not do the implementation by themselves. They simply copy from your senior students. It's meaningless at all. You need to grasp this chance. Try to do the coding by yourself. Try to enhance your programming capability, not just cut and paste. All right, so you need to design it. Think about the example that show up in the slide and plan your methodology. All right, so you are asked to design the computation logic or the crossover operator or the permutation encoded GA and display the logic in pseudocode. I ask you to write the pseudocode first. Okay, and then implement that pseudocode into your system. For all of this crossover operator, I ask you do the crossover as many as possible. Okay, if you do not do anything, then you will get a low score. And here I prepare a pseudocode. It's not the best one. You can always later on come out a better implementation or this partial recruitment somehow with many probably a minimum amount of memory usage somehow. This is related to the algorithm. The algorithm design somehow, right? So computer science guy, they really concerned about the computational capacity and the memory usage and operation times. All right, they always try to get a good algorithm, which is much faster and they use the less amounts of memory anyway. All right. So I ask you write similar to this this content. It's a pseudocode, okay, pseudocode. So I prepare a pseudocode for PMX, partially map crossover. All right. So what you have is pair one. Well, it's not directly. Okay, remember that it's not directly related to this function at all. Okay, because what we have here is the index, right? It's the parent one index, parent two index, child one index. All the data has been stored in the chromosomes, two-dimensional array, right? So don't mix up with the pseudocode and your real implementation code. It's just a conceptual pseudocode. We have parent one is chromosome. Right now it's an index. It's a chromosome. P1 chromosome, P2 chromosome, P2 C2 C1 C2 is chromosome. So the PMX right now I intended to do is right. Well, I prepare another array. N is another array. Okay, so MI is meaning that the mapping target of I. So the I's element, for example, if I is 1, okay, is 1. So meaning what? Meaning what we have is job 1. So job 1 will map to M1. Will be swapped with, anyway, the mapping, you see, if you still can remember, we have a test, right? We have a quiz on that. So the target, the I will map to the target should be MI stored in this one-dimensional array. Okay, so that is the whole meaning. So I1, I2 is the cut position because by default, right now, our PMX is just we're 2-point cut. But for general case, again, you might specify arbitrary cut. Okay, so I have one cut in I1, the other cut in I2, and I want to make sure the cut location I1 is smaller than the I2. So you see, pseudocode is just right here. If I1 greater than I2, then swap I1 and I2. So make sure I1 is always smaller than I2 anyway. And then M1 is an array, right? So initially I ask everything to be the -1. So that is the whole idea about pseudocode. Try to plan a computation procedure telling you that this will work. Once you complete, follow this step, everything will be okay. So and then for I start from I1 up to I2 -1. So that is the convention we use in C related C family programming language anyway. So if they are the same, P1 equal P2, next I, then next I, then next I. So it's quite amazing, quite similar to the coding. But anyway, it's a pseudocode, so it's not related to any programming language at all. I just tell you idea. I have an array. The notation I use is a right blanket telling you that. Okay. So for this part, if they are the same, we go to the next one. And if the map, you see, if the map of P1 is equal 1, pair 1, the pair 1, you see, this is pair 1's value, and M is the location. So pay attention to this array. See, later on you will see M, O, M, O, M, such kind of thing. All right. So behind this pseudocode, there is a certain kind of computational logic, right? So you need to design this logic first, and then you write down the pseudocode. And after that, you implement this algorithm in your code, in your programming language somehow. So for this part, I try to build a map, right? See, it's a map. So map is that if you bump into integer whose value is I, and then I look into the i's element on this map array, I know the target. I know the target of the mapping. Okay, that is the whole idea. I'm written down here. But you need to pay attention to this notation. M-O-M, see, it's M-O-M-O P2 O-I. It's kind of complicated, but you need to pay attention to that. So the first part, I try to build up a map array. If the value is less than 0, for example, -1, right? -1 initially let's say to -1, -2, -3, then there is no any mapping target at all. But if the value is not 0, that means I will map to MI. So I try to keep this. I try to find this map first, and then if I have this map ready, then it's very straightforward. See, or we try to generate a child right here, right? Generate a child here. Start from 0 up to n-1, right? Okay. If I smaller than the cup position, oh, excuse me, I made a mistake right here. That should be I1. Oh, no, it's okay. Okay, right, it's right. Excuse me, right. So if the I is the gene location is larger than I1, you see, this is the crossover part, right? When I is larger than I1 and smaller than I2, this part is flip over, right? Kind of crossover. So C1 will take the chromosome of parent 2. C1 will take parent 2. C2 will take the parameter of the parent 1. But for the rest of them, in the first part and the part, we need to check the map, right? So I will check if am I right? If the map target of the P1I smaller than 0, if smaller than 0, there is no any mapping. We directly copy from the parent 1. There is no any mapping, right? If the map value target is smaller than 0. Otherwise, if it is smaller than if it is smaller than 0, there is no any mapping. But if it do has a target value, right? So C1 will use parent 1, the target of the parent 1. Initially, see, C1 assigned with the parent 1, right? But right now, if this P1 has a mapping target, now I use that mapping target to assign to the child 1. So the algorithm-wise is very straightforward, and I think this pseudocode has been approved by my code, so it should work correctly. If you blindly implement this pseudocode into your code, it will work anyway, right? But you need to design this pseudocode for the rest of the crossover operator. You need to do that by yourself. I ask you to think about the procedure, write down the pseudocode, get some exercise, and then implement your code. And you need to debug it. Okay. So that is the partially map pseudocode. You can try it. And probably I should use one example to show you what I have in my mind in this pseudocode. Okay, I will try to explain it and somehow use the previous slide. Okay, let me go back to the slide we have. I cannot see. Let's be. So computing that should be 5 or 4, 7. I don't have it. I don't have it. Okay. Crossover should be 7. I don't have it right here. And I do have some information ask you that do not have a new statement specified within crossover or mutation. Do not use new. So if you need a data structure to help you to do the job, you prepare that array, especially a dynamic allocated array, outside the function. Prepare that in advance. And then allocate the memory once. Otherwise, you will, because the crossover operation will be invoked repeatedly, right? And if you have a new statement specified within this function, then the new operation will be repeatedly invoked, and memory will be used up. That will slow down your computational speed too. So prepare your algorithm first, and then if you need to use a dynamic allocated memory, try to allocate the memory outside this function just once before you perform the crossover operation, and allocate enough size of the memory for your usage. Okay, remember that. All right, so the whole idea. This is the genetic algorithm. Okay. Okay, so as you can see, we have two PMX, OX, position-based, order-based, CX, subtool exchange. We have this crossover, and also we have different kind of mutation, right? All right, so I use so what in my pseudocode I try to, well, for example, right now we have pair 1, pair 2, but I just use one array. I prepare what I need. The data structure what I need is an array. Okay, I call it M array. I will use this example to show you the procedure, what I have in my mind. So initially this is called map array. Initially it turned out to be -1, -1, -1. Remember that the index starts from 0, right? 0, 1, 2, 3, 4, 5, 6, 7, 8. So as you can see, eventually we need to find out, well, if it is 7, right? If it's 7, oh, okay, 7. Right now we have mapped to 7, right? Exactly 7 right here, right? It's 7. And eventually, the content is 4. 7 is 4. So 4 should be 7. If I prepare this map within this M array, so it will appear like that. This is 4, this is 7, and that should be 9. Oh, excuse me. Okay, forget it. What can I do? Do I have eraser? No. Well, I will re-index that because this example always starts from 1. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 7. Whenever I want to build up this mapping somehow within this array. So 7 mapped to 4. So that should be 4. 4 should be 7. 9 should be 3. 3 should be 9. 6, 8. 6, 8. 8 should be 6. And the rest of them probably should be -1 or -2. I don't care. So if I finish this mapping, this map construction, then I can perform the crossover very easy. So right now it's 1. 1 is -1, right? Directly copy to the child 1. 2, -1, directly copy to 2 there. And this part is fully over, right? It's swap, from child, so I'm not going to take up How about 7? So check the 7, check this M5. Okay, 7, it is not less than 0, so it's 4, so I need to change it into a 4. 7, change it into a 4, put it in here. And 8, check 8. Oh, okay, 8 should be mapped to 6. Let me check. So 8, 6 right here. How about 9? 3, change to 3. So if I have this M array ready, I can directly perform the crossover, right? Partial crossover, right? So, but the problem is that how can you build up this map array? So let me show you step by step. Okay, how can I do it? So initially, I should what should I do? Okay. What should I do? It's kind of crowded, so I had better we do it again. So probably within pen. So how can I build this map? I'll show you. Oops. Okay. So remember that right now it's 1, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So initially, I make everything -1, every value -1. Okay, so the first pair, when we are trying to build up the map, right? So the P1 is 3, P2 is 5, 3 and 5. So I came to the 3, check M3. I need to check M3. If it is -1, and how about 5? 5 also -1. So the case is that both of them are -1, right? Both of them are -1. So if both of them are 1, I directly write everything, write the value to each other. So the 3 I will update into 5. Since both of them are -1, 5. And that should be 3. So we kind of form out a pair, right? A pair of map, 5 and 3. All right, so it's done. How about 4 and 7? Okay, 4 and 7, another pair. Okay, I check the 4, the value -1, 7 -1. Oh, okay, the same. The situation is the same. So I perform well. I just set the value with each other. So 7, put in there. 4, there. It's quite similar, right? So we kind of build up this mapping relation right now. 4 and 7. And then for the next pair is 5 and the 9. But this time, you see, it's not -1, right? 9 is -1. So another case, 1 is -1, the other is not. Similar, in another case, it should be one of them is -1, the other is not, right? Which means that we will join another pair. So you should pay attention to the implementation carefully right now. So right now, the -1 should be the one already has right now is 5, 9, right? 5, 9. The one has the value there. So we check this value. Okay, we check the value. Oh, okay, value is 3. This one is -1. Our target is 3. So we check this guy 3. We know that current is 5, right? Right. So we allocate this place right now. This place 3 place right. But right now the target turned out to be 9 and this target, not 9 and 5. The pairing wise should be not 9 and 5, but it's 9 and 3. So 9 and 3 should swap each other. So and then we know it's 3, right? It's 3. So we change the -1 to 3. We updated this guy from 5 into 9. And then we change the original, the middle one, 5, into -2. You can change it back to -1, it's okay, but I prefer that where I put it in -2, saying that where it has been joined somehow by another pair. So we change it into -2. Let me write it in like that, -2. So 5 no longer appear on a pair, right? It's same because initially we have 3, 5, 4, 7, right? But find 9, right? So find 9. 5 should be invisible right now. It has been combined. So right now it's 3 and 5. So 3 and then 9, right now they are paired. They're paired. For the first one, 6, 8, right? 6, 8. So we check 6. Oh, okay, it's minus 1. 8 is minus 1. 6, 8, right? 6, 8. Well, so we have 6, 8, right? So it's simple. Well, we just simply change the map with each other, right? So 8, there should be 8 and 6. Okay, I think that's it. But for this example, we did not bump into this situation. Both of them are none, right? Both of them are not equal minus 1. So in this case, we need to, well, that should be in the similar way, right? So these two guys, I do not have this example shown up here. I had better let you study by yourself, okay? If both of them are the same, so definitely we check each other, right? This example is, I don't have this example ready, so. Well, the idea is that, suppose right now we are talking about 4, 6, okay? We're talking about 4, 6. And 4, 6 right now they have their own mapping target, right? 7 and 8. So we need to set another position. The idea is that both of them are not equal minus 1. So we check the 7. We check the 8. We check the 7 and 8. I think it should be right here, right? 7 and 8. So meaning what? So initially 4 is mapped to 7, right? Initially 4 mapped to 7. And 6 mapped to 8, right? But right now we have a new pair. We have a new pair. 6, not 6, 8. 4, 6. We have 4, 6. We have 4, 6. For example, we have 4 and 6 right here. 4 and 6. 4 and 6 right here. So 4 and 6 is our parent. 4 and 6 are parent, but they have their own mapping target, right? So the same again. We identify this location, right? 7 and 8. 7 each other, right? Okay. So right now it's 7 and 4. Oops. Ah, gosh. Come. Okay. I have here. So right now, we already have 4, 7, right? It has been spread there. 6 and 8 have been there, but right now we have 4 and 6 pair right here. So we identify these two guys, knowing that both of them are not equal minus 1, and then we try to rebuild it. So go to the other side 7. The other side is 8. So 7 and 8 right here. 4, 6. So it's pretty simple. I mean, go to the first one 7, and the second one. So replace with this guy with another guy. So we change it to 8. The other guy into change to 7, and then for both of them, change into for me I change it to minus 3. So you see 4, 6 right now has been merged, right? 4, 6 has been merged together, right? Because right now we have a new pair of 4, 6, right? So 4, 6 combine these 7 and 8 together. So what's left should be 7 and 8 mapped. 7 and 8 mapped. So I'm kind of carrying out this kind of procedure, try to preserve a final map in this M array. That is the whole idea I have. So I do not renew anything. I mean, I did not repeat any new statement within this crossover. What I need is that I need an array for me to use, and the size can be allocated only once in advance before I do the any pair or crossover operation. So I keep reusing this memory. Once a pair or parent came in, I keep using this one, so it's okay. So I did not have a memory overflow at all. So all these procedure has been written down in pseudocode first, and then I think it will work correctly, and then I implement the code to your code. So we can follow this pseudocode, try to implement partially map crossover. All right. So that is a mission. So So in this case, if we go back to our code, all right. So what I have in the permutation, partially mapped crossover, what I need. So what I need, maybe I need an int array m. I defined it outside. Don't new everything within this function, because this function will be repeatedly called. If you need anything, prepare data in your class, this class, prepare that. So remember that right now for my PM partially map, I have m array. It can be shared by the other operator. Okay, don't add a bunch of data unnecessary, right? This data, if it exists within this class, it can be shared, can be reused by other crossover. Okay, because only one type will be invoked, right? Okay, so I have m ready there. And when will you need to initialize it? M is related to what? Related to number of chromosomes, right? So I need this guy, and I know the size of this guy can be initialized right here. M equal new number of variable. It's related to number of variable, right? It is not related to population size at all. So this array, the size is fixed right in the constructor. That's it. So M will be repeatedly used by different kind of. Remember that in your orders, you still can use this array because it's just an array or number of chromosomes lengths. The length is fixed there, so you can reuse that. So what I'm asking is that you look into the example shown up in the slide or the restore operator. Try to write the pseudocode first and then implement it in your system. Don't just go back to copy previous students' work. Do it by yourself. I like to see that. So what I'm expecting that if you do submit one pseudocode for an operation, then I think you have done that. So not just copy all the crossover from your previous senior students and then saying that, well, your system has this kind of capability. No, if you the grading will based on the pseudocode you submit. Okay, since you will write a pseudocode, I know you implement that by yourself. So I will give you score. I will give you grade. All right. So don't copy directly from your previous student. No, do it by yourself, and then build up your programming capability. Because later on, if you see different kind of meta-user algorithm paper, they just saying this kind of operation, you need to know how can you implement that by yourself. All right. So is there any question about that? So you need to implement this generate pair crossover the children. So similarly, you need to override another one distributor. We are not going to perform the mutation operation by ourselves, okay? But we just want to generate a mutated children. This one, we like to implement that. So similarly, well, if you look into the slide, how about the mutation? So mutation-wise, we have probably the easiest one. Okay, thanks. Reciprocal exchange. Actually, that is swap. Okay, reciprocal exchange mutation. Well, actually, that is swap. Okay, just arbitrarily select two gene, right? Two position, and then flip open. Swap the gene value. That's just simple, right? Reciprocal exchange. So here, because this function has provided a PID for you, a try ID for you, right? So again, I need to switch. Blah blah blah. See, I did not do that. Okay, so you need to do that. So what I'm implementing right here is for so-called swap. Right? I can call it swap somehow, swap method. So how can you do that? Well, actually, it's simple, right? Chromosome 4, INT, I start from 0, I start from number of genes, right? Number of genes up to this place, right? And before that, I might ask randomizer, RA. Do I have randomizer? IND? No. IND? No. Oh yeah, we have. We inherit this randomizer, right? Next, PID, no, number of gene, right? Number of gene. You can prepare, well, if you don't like to set up a lot of local variable, right? You can probably set in outside PO, position 1, position 2, because we are dealing with the permutation GA. So we are not going to allocate any local variable. Oh, still okay, and you still can special local variable there. But if I special outside there, so that can be shared by crossover and by mutation operator too. So I have position 1 randomizer. Next. Oh, okay, excuse me, right here. POS1, POS1, right? Position PO1, okay, PO1. And PO2, again. So I'm not going to do all the rest of them because PO2 should be different with PO1. Okay, so you need to do that. You need to do that by yourself, okay? All right, so so chromosome, CID, right? Gene position, I. Normally, that should be copied from parent, right? PID, I. Right? But if position, if I exactly equal PO1, right? Excuse me, PO2. So the algorithm turned out to be very simple. Right? So the crossover is actually so in position 1, you use the position 2 gene. Using position 2, use position 1. Wow, that's it. It's so simple. So remember that it's just a mutation for the swap. So you need to implement the rest of the mutation operation there. So we are dealing with so-called chromosome-wise mutation. So we take one parent, try to change some gene, send them back. But not send them back, just create children from parent. It's much more simple comparing with the binary GA. Because binary GA, we kind of perform the gene-wise. So we need to simulate the location of mutated gene. Okay. And I think that's it. So permutation GA probably the hardest part should be here. I mean, the permutation partially mapped, and you need to make sure everything is okay. Okay, so you should check the children somehow. You need to debug it either way by visualization or try to write a program, a small program to check every instance, every integer number appear exactly once. And then if nothing happens, it's okay. If for example, number 1 appear more than once, then you will flag back saying this children is not legal somehow to help you debug your code. It's likely that you have a bunch of bugs implementing this crossover operation, right? But just stick on it, learn it, improve, enhance your programming capability, okay? All right, so I think that's it. I don't think there's any else I need to add. So what you need to do is that complete this enumeration, right? We have the rest of the crossover, and also create a new one for mutation. So both of them will have a property specified within your permutation GA. So in addition to the crossover type, we will let the user choose a permutation type. So once mutation type has been selected, well, we will perform different kind of computation. Try to complete children 1, children 2 for the crossover operation. Try to achieve that mutation. Try to achieve that. Okay, I think that will be all. Do I need to override anything else? No, that's it. So it's very simple. So later on, I mean, if you have time, or probably after we are when we are doing probably assignment 11 or 10, we have a problem, real number optimization problem. Real number optimization, that means your variable are real numbers. So in that case, you come back to your GS solver, try to add another GS solver. We call it a real number GA. Try to implement that. And then you will have a powerful tool, automation tool, okay, for all kind of automation problem later on. All right, so okay, I think that will be all for today's lab. So, well, I will try to prepare this video and put it into the web. But I think it's so straightforward. You should do it by yourself. But you need to study. You go back to the slide, study those examples, prepare your pseudocode first, and then implement, debug it. That you will, I think your programming computer will be greatly enhanced. All right. So don't bother about copying other work from other students. What you need to submit is the pseudocode. I like to see the pseudocode. Pseudocode have a different kind of pseudocode does not have any standard format anyway. When you read through it, it looks like a code, but it's not real code. Okay, it's just you can explain the procedure clearly. That means for you reader, and that will be the good pseudocode anyway. So you can write your pseudocode in your own way, not just for you don't need to follow the exact formula I'm using in the instruction. Okay, this instruction is I think usually for pseudocode we kind of use this arrows signal, meaning that assignment, right hand side will assign to the left. So that will always should be the variable in it somehow. So you can use the string. You can use the string or any formal sentence to explain what you were going to do. Don't bother about detail for a lot of things there. All right? So if one line can fully explain what you were going to do, then just use one line will be enough. Okay. All right. So that's it. We end up today right here. So if you still have a problem, you can stay here, and I still have time to help you. Okay, so that's it. So finally, reminding that you need to do that and start as early as possible because the deadline is still on Saturday. So I expect probably you will spend a lot of time in implementing the crossover, all right, and preparing the pseudocode. So do the assignment as soon as possible. Okay, that's it.